Good morning. My name is Yue Shao, a fourth-year PhD candidate at the University of Wisconsin-Madison under the supervision of Professor Victor Zavala. Today, I will present our work on modularity measures, concepts, computation, and applications to manufacturing systems. The main takeaway message in this talk is that we proposed a measure to quantify the modularity of industrial production systems using graph theoretical tools, and also propose the optimization formulation to compute it. Let's first talk about why we want these manufacturing systems to be modular. For a modular plant, the project startup time is minimized since systems can be fully assembled and tested before they ship, reducing the amount of on-site construction time. Weather delays are eliminated during process system development since modules are assembled indoors. Lower labor and operational costs are achieved due to a shorter project timeline, efficient use of material, and a smaller field crew. Also, offset module construction does not interrupt or shut down pre-existing operations. They have small investment risk, increased reusability, and a flexible capacity amount. They are popular because they fit in today's market as it has shorter product life cycle period. However, in order to design a modular plant, we first need to have a quantifiable measure that tells us how modular is it. But in the context of manufacturing systems, such quantifiable measure is missing. So the natural next question will be, what is modularity? In traditional graph theory, a network is considered modular if the connectivity within modules is much denser than that between modules, like the two graphs shown below. On the left, you have a modular network in which the number of edges within the three modules marked with different colors is much greater than the number of edges between them. But on the right, you can't really tell if such relation exists. Within the field of graph theory, multiple modularity measures exist, and one of the most popular one is proposed by Newman. It is defined by comparing the density of the internal module edges relative to those found in a random graph. And the random graph can be obtained by starting with a set of n isolated nodes and adding successive edges between them at random. The two figures below. On the left, you have a random graph where no subset of nodes exhibit any structures. But on the right, you can clearly observe that nodes 1, 2, 3, and 4 are tightly bonded to each other, and nodes 6, 7, and 8 are bonded to each other as well. Continuing with Newman's modularity measure, we define a set V for all nodes and the total number of edges as M. We define the degree of node I as Ki, which is the number of edges connected to a node I, and adjacency matrix A with entries AIJ. Then the expected value of the number of edges between nodes I and J, defined as Fij, can be calculated as Ki times Kj divided by 2m. And the modularity matrix B with entries Bij is defined as Aij minus Fij. If we further define a membership matrix delta with entries delta ij such that it equals to 1 if two nodes belong to the same module and 0 otherwise, Newman's modularity measure can be obtained by solving the following maximization problem. It is a powerful modularity measure in graph theory, and it performed well on many network benchmarks. But is it suitable in the context of manufacturing systems? In manufacturing systems, other than the connectivity of modules, we need to consider a little bit more. First, the size of the modules. The benefit of modular plants, such as shop fabrication, can only be possible if those modules are transportable using available infrastructures, such as railways and trucks. Second, some people may prefer a small enough modular system that can be completely assembled off-site, packed in a single module, and transported to its final destination, while others may prefer a system with a larger number of modules in order to assemble individual modules at different locations. Eventually, the comparison against the random graph in Newman's measure is not intuitive in the context of manufacturing systems. Therefore, we would like to propose a modularity measure in the context of manufacturing systems that not only satisfies the modular characteristics defined by graph theory, but it also incorporates all those perspectives that I just discussed, dimensionality requirements and flexible number of modules. Let's first look at some notations and definitions. The graph is defined similarly as in previous slide. And we further define a set of modules C and the number of modules as T. We use Ci to denote the module that node I belongs to. Now the module membership matrix delta can be defined such that delta ij equals to 1 if Ci equals to Cj and 0 otherwise. The key property of this membership matrix delta is that the rank of the matrix equals to the number of modules. Here is a demonstration of the membership matrix. We have a small network with 5 nodes and some edges represented in the adjacency matrix A. The figure on the bottom left shows the membership matrix for this graph if it is divided to 2 modules, node 1, 2, 3, 4 being in the same module and node 5 in its own module. And the bottom right figure shows that if each node belongs to a different module, the membership matrix is just an identity matrix. The coverage of a graph is defined as the density of internal module edges relative to the total number of edges, and it can be calculated as the membership matrix delta times the adjacency matrix A. Eventually, our proposed modularity measure with T modules is a maximization over the graph coverage with a constraint on the number of modules. Back to the example we just saw, if we want 2 modules out of this network, like shown in the bottom left figure, the modularity measure is 4 by 6, which means that 4 out of 6 edges are within modules. And if we want 5 modules instead, like in the bottom right figure, the measure is 0. All edges are between modules. Now with this new definition of modularity measure, we proposed an optimization formulation to solve it. We define the binary variable matrix X with entries xik such that it is 1 if node I is in module K and 0 otherwise. The module membership matrix delta with entry delta ij can then be represented as sum of xik times xjk over the module set C. And each node may have some intrinsic features such as its dimensions. We define an upper and lower bound for all those features. With these definitions, here is our optimization formulation for calculating the proposed modularity measure. The objective encodes the connectivity of the graph. The first and second constraints are logical constraints, and the last constraint is the dimensionality constraint that can be used to enforce transportability of a module. And the rank constraint is embedded in the dimension of binary variable X. This formulation is a mixed integer quadratic program. As we will show in the case study, we can solve this problem without the rank constraint to find out the intrinsic module divisions, or we can solve this problem with enforced number of modules to explore different module compositions. It turns out that since our quadratic term is binary, we can apply a small trick to do some exact reformulation of the objective term to show that this quadratic objective is actually convex, which makes this problem solvable by popular solvers such as Gurobi and also scale well for larger graphs. Here, we used an example of a dimethyl ether production process from methanol to illustrate the key points of our proposed modularity measure. Intrinsically, the process of production of DME from methanol can be divided into 3 logical subsections: the feed and reactor section, the DME purification section, and the methanol separation and recycle section. The process flow diagram and the subsections are shown here. If we regard each equipment, the feed and the product, and flow junctions as nodes labeled with numbers, and each flow stream as a directed edge, a block diagram can be drawn on top, and we can further convert it to a network representation like shown at the bottom. This network representation encodes the size of each equipment. For example, some larger nodes like node 8, 23, and 14 represent some larger equipment such as reactors and distillation columns. If we want to modularize this process into several modules, these larger equipment might need to be separated into different modules in order to satisfy the dimensionality constraints. We first computed the modularity measure while ignoring rank and dimensionality constraints. In this case, each node does not have any features to be bounded, and we let the program to decide the optimal number of modules. As expected, the solution of this problem gives a modularity measure of 1, which means that all nodes are assigned to one module. We then computed the modularity measure by setting the rank T from 1 to 6. The results are summarized in the table. We can see that as the number of modules increases, the modularity measure decreases. Multiple configurations can give the same modularity measure, and the number of alternative solutions increases sharply with increasing number of modules. For a configuration with T equals to 6, 87.5% of the edges are inside the modules, while 12.5% connect the modules. Then we computed the modularity measure by considering dimensionality constraints, but ignoring rank constraints. So each node now has their sizes, and we still let the program to choose the optimal number of modules. Here we explore the impact of scaling up the process and set the minimum dimension of each module to 20 and the maximum dimension to 40. We observe that dimensionality constraints induces an organization with T equals to 3 modules, and the associated modularity measure is 0.925. Only 7.5% of the edges connect modules. The resulting modular organization, as shown on the right, is the same as the intrinsic functional organization shown in previous slide. This highlights that practitioners use natural logic to modularize systems, and the proposed modularity measure is intuitive. Here are some conclusions and future works. In this paper, we discussed key characteristics of modular manufacturing systems and proposed a modularity measure and a corresponding optimization formulation to solve it. We performed a case study to show that the proposed measure is intuitive. In the future, we would like to use a proposed measure to guide the synthesis of systems with desired properties and explore computational strategies to analyze large-scale graphs. Finally, I would like to acknowledge the National Science Foundation for funding this research project. That is all for today's talk, and I'm glad to answer any questions.